actually did this on Friday, okay? This one's not a new one for us. So this ties into my table talk. It asks you to write the equation of the cubic polynomial shown. So what should be my first step? Yeah, Avery? Awesome. Yeah, you're going to find your x-intercepts. So that's crossing at -1, 2, and 3. Okay, so we're going to identify your x-intercepts. Then you're going to begin the factored form. Let me repeat that. When you have a graph of a polynomial and you want to write the equation, your first step is identify the x-intercepts. Your second step is write the factored form. Then I'm going to circle back to what Becca helped us with the table talk, is now you're going to pick a point. And do you see in this one, there's one labeled for us? We're going to use 1 comma 8, I'm thinking of what I'm writing, to find the a value. So my x is 1, my y is 8. I'm going to pause a moment and give you a head start. Plug in y is 8, x is 1, and solve it for a. Are you getting a is 2? Then here's, don't stop there. That's not the equation. That's just my a value. And then I'm going to go plug it back in. Questions? Anything that I can clarify for you on this type? Do you understand that I could have it? If we jump down to example 7, let's jump there first. Example 7 says write a cubic function with x-intercepts -3, 0, 1, 0, 4, 0, and passes through the point 0, 2. Do you see that example 7 is in fact the same as example 5? So what would I do? I've already given you the x-intercepts, right? So what should be the first thing I write down in example 7? Yeah, Angelo? Okay, before I get there, could we do one thing before that? Could we write the factored form? And then, absolutely, I'm going to do what you said. So if you know x-intercepts, let's write the factored form, and then let's do what Angelo suggested. Because what you're trying to do when you're working problems is not just get answers, we're really interested in demonstrating our thinking. What were you thinking? What do you know? What knowledge do you have? When you know x-intercepts, we immediately know the factored form. So then let's plug in 2 equals a times 0 plus 3 0 minus 1, 0 minus 4. Now, do you understand it doesn't have to be the y-intercept? Like in example 5, I had the point 1 comma 8. I just need a point. So if I divide by 12, a is a fraction, right? And that's okay to get a fraction. So my equation is going to be y equals 1/6 x plus 3, x minus 1, x minus 4. So let's jump back now to example 6. If I ask you to convert to general form, watch what I'm going to do. I can distribute and make that 2x minus 2. And I can take x plus 3 squared and make that x plus 3 times x plus 3. I cannot multiply 3 things at once, but I can multiply 2 at a time. It does not matter the order you choose, but because I know x plus 3 times x plus 3 is a perfect square trinomial, I'm going to do that first and say that's x squared. And remember, we've talked about this. Try to do the outer and the inner in your head. 3x plus 3x is 6x. Otherwise, you're always going to have one extra line of work to do. Then we're going to use the extended distributive property. I'm going to take 2x times the trinomial, and then I'm going to take the minus 2 times the trinomial. Again, I'm taking the 2x times the trinomial, and the minus 2 then times the trinomial. Then we'll collect like terms. All right, somebody showed me this today. Let me try it. Look at that. One of the math teachers showed me that today. Ah, isn't that cool? That's super cool. Way better than my handwriting. All right, let's write down here. I don't know if it knows what to do with the box, but we'll try it. Well, yeah, I don't think it likes mine. All right, doesn't work all the time, but that's really neato. Okay, all right, so who cares? Who cares about this? Well, in the real world, we use these skills to help us maximize or minimize volume and surface area. So let's look at an example. In example 8, it says a 5x7 piece of paper has squares of size length x cut from each of its corners, such that it'll fold up and will create a box with no top. So watch what we're going to do. So I didn't draw that very well. Let me try this again. 5x7. So this is 5 and this is 7. And what they're saying is you're going to cut a square that's x by x from each of the corners. And then it folds up to make a box. And it says find the value of x that would maximize the volume. Well, this is a box, so we know that boxes have volume of length times width times height. So my length is actually 7 minus 2x. My width is 5 minus 2x. And my height is x. Now if I can grab a piece of paper and kind of show you this. So watch, if I take, this is just a regular piece of paper, and if I cut, now this won't be perfect, I'm just eyeballing it. So if I'm cutting, do you understand then, if this were 5 across, I took x and x off, so that made it 5 minus 2x. And then on the long side, that was 7. This was 7, but I took an x and an x off, so now this piece is 7 minus 2x. So do you see how I've made a box? And it really is 7 minus 2x and 5 minus 2x. Does that make sense? How I did that. Okay. So let's go ahead and let's multiply it out. This is 35, and maybe I'll put the extra step in. This might be a little bit harder for us. So I want to talk a moment about domain. Remember, what is domain in general in algebra? What was domain? Remember we talked domain and range? So what's domain? Yeah, it's the allowable x values, okay? So I want you to think about this. Could x be 0? No, because that means you'd have no height, right? X is the height. The x value I cut off is what I would fold up. So this has a height of x, so it can't be 0, okay? Now, I want you to think about let's do the 5 minus 2x, okay? If I take 5 minus 2x, what's the biggest value x could be so that it doesn't take up the entire half side, you know what I mean? So like, could x be 1? Could I take 1 off of each side? So instead of this being 5, it's actually now 3, right? Could I take 2 off of each end? Yeah, it'd be pretty skinny, wouldn't it? If I took 2 off of each end, 5 minus 4 is 1. Could I take 3 off of each end? No, then I have a problem, right? Because that's more than my 5 if I try to take 3 off. Where's the maximum that I could take off? 2.5, but I really couldn't take 2.5, right? Because then there'd be no width. So here's my domain. My domain has to be a number between 0 and 2.5, but not 0 and not 2.5. Do you understand why I chose that side instead of the 7? If I tried 7, I could have done 3 off of each end, but that didn't work on the shorter side. So I went with my shorter side. Okay, so now I'm trying to find what x would be that's going to be between 0 and 2.5 that would give me the maximum volume. We actually can't do this one algebraically, so watch what we're going to do. I'm going to grab my Desmos, and if you have a graphing calculator, you could do that or just watch me. This is going to go y equals 35x minus 24x squared plus 4x cubed. Okay, so do you remember how I said this had to be a number between 0 and 2.5 for x? And then do you see that there is a little maximum point there between x is 0 and 2.5? And its x is 0.959. So you would look at the graph to see where there is a maximum value in that region. So let me come back to the notes. And so on the graph, it was 0.959. That is the x value that would maximize the volume of this box. So this is where you would use what we're doing. Maximizing volume, you can minimize surface area of, say, a soda can. You might want to minimize, like Amazon, might want to minimize the surface area of its boxes because that'll cost them less money with their shipping. All right, in example 9, I have factor completely over the complex numbers. And I want you to notice that I put complex, which means, what does complex numbers include? Imaginary. Okay, so in letter A, step 1 is GCF. What's the GCF in part A? X. I can't go any further. That's it. Now, these next two, when you do complex numbers, I actually can factor x squared plus 16. It's going to factor into x plus 4i times x minus 4i. So do you remember that in chapter 5 where I gave you a complex 0, you came up with the conjugate, and then I had you write the quadratic equation. So then watch this third one. If I wanted over the complex numbers, I could do x plus square root 11, x minus square root 11. All right, I'm going to give you a head start in example 10, and I want you to use that extended distributive property. And while I'm giving you a head start, I have a special tool in my math tool belt. I haven't had my tool belt out in a while. Usually only comes out once a quarter, so this is one of those special occasions. And I think I pulled the tool out, but you had to wait to find out what it was. Here's the day. Hold on. Ready. Oh, there. I have a special tool, it's a bar of soap. Oh, you this tool. Ugh. Okay, so I'm going to distribute. I personally like to take, when it's a binomial times a trinomial, I'm going to take x times the trinomial minus 2 times the trinomial. You can do the binomial times each individual term. That does the job too. So I'm doing this first. So I'm going to get x cubed plus 2x squared plus 4x minus 2x squared minus 4x minus 8. Now let's use my last one. Beautiful. Okay, so do you see what happened here? The x squareds canceled and the x canceled. This is leading me, dun dun dun, to a sum and difference of 2 cubes. And we are going to use a technique called SOAP. Okay? And I have a cute little story to tell you. This is from my oldest son is 27, and so this bar of soap is like 20 years old. If I ever opened it, I think it would disintegrate. But this bar of soap is literally 20 years old. We love going to, my family loves doing the Ohio State Fair. And so one year when we went, you see there's this little green glob, and that was supposed to represent a bacteria. And so there was a person dressed up in this big green glob passing out soap. And it fights bacteria by washing your hands, okay? Well, my oldest son, Andrew, he was petrified of this person because it was like this big, green globby coming out and, reaching out and trying to hand us things. And he was like holding on to the back of my legs for dear life. He was so scared. And I just love this bar of soap. It reminds me of that time at the state fair. But anyway, here's what I want you to know about soap. This is our last technique of factoring. And so do you see when I have a cubed plus b cubed, you find the cube roots. So it's the same sign. Then you square it. It becomes the opposite sign. And then it ends always positive. So I want you to kind of look backwards at this one that we did. Do you see that x is what's getting cubed? So I put an x in. When I have 8, it's 2. It's the same sign here. Then you square it. Then you take the x times the 2 is 2x, and then you square the 2. The same, opposite, always positive handles all the signs that you need. So then look here. This was a minus, so this is a minus. This is now the opposite, and always positive. So what are cube numbers? 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, 7 cubed. Oh, I don't know 8 cubed. I know 9 cubed. Somebody do 8 cubed for me. I forgot that one. 8 times 8 is 64. Well, I can figure it out. 512. Thank you. All right, so these are the first 10 cube numbers. So here we go. We're going to use soap. So this is x getting cubed, and this is 5 being cubed. So soap says I put x minus 5, same sign. Then I just square the x. I take the opposite sign and take the x times the 5, always positive, and then I square the 5. All right, you try the next one. Figure out what is being cubed, and then try to put it in the sum and difference formula. Yes, you do have to remember this, but I think if you can remember soap, then you'll be fine. All right, what cubed is 27x cubed? 3x, right? That's 3x. What cubed is 64? 4. So here we go. It goes 3x. It's the same sign as this one, okay? So it's a plus. Then you square the 3x. I do the opposite sign. I take the 3x times the 4x is 12x. Always positive, and then you square the 4. Do you need an extra one? Do we need one more? Yeah, let's do another one. I agree. Let's see if I can make one up. All right, try this one. 8x cubed minus 125. Try this one. While you're doing that, I'm going to read off the final paragraph here. Most mathematical functions commonly used by engineers and scientists can be approximated by polynomials. A precursor to the computer, a difference engine is an automatic mechanical calculator designed to tabulate polynomial functions. Engineers use rational functions in their cantilever engineering projecting beams that are supported at only one end, like the sky deck in the Willis Tower in Chicago. The functional response curve is used by ecologists to describe the interrelationship of organisms, like, oops, and I didn't put a picture in, did I? Of the red panda and the amount of bamboo in a forest. So polynomials are huge in the real world. So here we go. This is going to be 2x is being cubed, and this is 5 being cubed. So I go 2x minus 3, same sign, square it. Opposite sign, and then you take the 2, whoops, where did I put the 3? Hold on. Sorry about that. That's a 5. 2x minus 5, sorry. Then I'm going to take the 2x times the 5, which is 10x, plus, always positive, and then you take your 5 squared. All right, show me thumbs. How do we feel about factoring soap now? Yeah. Okay, so do you see the formula here? The formula says once you get the A and the B, so now you're not looking over here anymore. You only look at this A and this B. You square what's in the first spot. Then you take A times B, what's in the first spot times the second spot. And that's why we're putting this. This is the A and the B. Okay? All right, let's do another one because I saw some thumbs down. Thumbs down. Let's do 64x squared plus 343. Okay, try this one.